Okay, so we got past two sets of electrons here. Get everything right so you can see it. Two sets of electrons around our central atom. We really just have one option there, linear. Now, what I'm going to try to do, so I think for study purposes, it'll be easiest if you just have one table here, but to try to keep everything close to my headings and keep it all in the video so that it's a little easier as you're watching, I'm going to flip over here and use the other side of the paper. And I think I'll probably try to keep doing that. But for your purposes, maybe having all this on one piece of paper might be good in terms of looking back on this and studying. But of course, the next thing we would need to consider is the next highest value in terms of sets of electrons. So what if the central atom in the molecule we draw has 3 sets of electrons? Now, things are going to get a little more complicated here because we now have 2 possible options that we might need to consider. And I'm going to put kind of parentheses and then a sub set of information here. And for the first one, I'm going to put 3, 0. And what I'm indicating here is, as we said, a set of electrons could be bonds, right? It could be a single bond, a double bond, triple bond. A set of electrons could be a non-bonding pair of electrons or a lone pair. So with 3 sets of electrons, we could still have a meaningful central atom, 3 bonds, 0 non-bonding pairs, right? But the other possibility we'll see for 3 is 2 bonds, 1 non-bonding pair. Okay, and these are going to encounter some differences as we go through all of the bits of information we can get about the structures. So keep that in mind, that the number of sets of electrons, there are more than one way to make those up depending on the amounts. Now with 2 sets of electrons, if one's a lone pair, that's not really a central atom anymore. We're back to kind of a diatomic molecule, right? Which is not something we need to put a lot of thought into the structure of. Okay, starting with 3 sets of electrons, they're all bonds. The point drawing there, right, we'd have our central atom, right? Now these 3 sets of electrons are going to spread as far away as they can. Well, that shouldn't be too hard to imagine. If you've got 3 things and you want to spread them apart, the furthest apart they can get would be the corners of a triangle. So this molecule might look something like that. Right, so now these electrons, this set of electrons has gotten as far away from the other 2 as it can. You move any one of those and they would start to encroach upon one of the other sets of electrons. So the shape here will look like that. We would describe this electron geometry as trigonal planar. Right? Now that's really a fancy way of saying it's a triangle, right? Gon is for side, so this is a 3-sided planar object. That's the same thing as a triangle. I don't know why it got labeled trigonal planar, maybe to make it sound more complicated, right? But that's the way it is. It's trigonal planar is the way we describe this molecule. And you have to have both of those. If you just say trigonal, that's not enough information. We'll see there are others that have trigonal in their name. And if you just say planar, that is not enough information either. It's got to be both of those. Trigonal planar is your structure. And probably worth noting as well, I am usually writing these in adjective form as if it's describing the noun shape. This is a trigonal planar shape. The shape itself would be a trigonal plane in the noun form, right? So sometimes people get confused by that, particularly when we get into some of the newer shapes you haven't heard of before. Tetrahedral, that's adjective. Tetrahedron, that's noun. But they're both describing the same thing. Now, probably familiar here, this would be a equilateral triangle, the way it's drawn here. So the bond angles here between those things. Well, actually, probably thinking about the equilateral triangle is not so helpful. All the way around the circle is 360 degrees. So there's 3 segments here. So these bond angles are all 120 degrees between those lines. Okay. Now, all the bonds, all the sets of electrons are bonds. We said that means the molecular geometry will be described by the same term as the electron geometry. So the shape here, or molecular geometry, is also trigonal planar. right? And an example here, kind of the straightforward example would be for a boron compound. So if we have something like BF3, right, that's boron in the middle, 3 fluorines attached to it, and each of those fluorines would have a complement of non-bonding electrons to get up to an octet, right? The 3 sets of electrons around that central boron. You could also end up with a central atom where you have a double bond and 2 single bonds. So something like H2CO, the carbon in the middle would be double bonded to the oxygen, but then have single bonds to the 2 hydrogens, right? And also 2 lone pairs on the oxygens. So this carbon as well would have 1, 2, 3 sets of electrons. So you'd have your 120-degree bond angles, and you would have a trigonal planar shape here for this molecule. Okay, now the other option, so 2, 1, this would be 2 bonds, 2 sets that are bonds, 1 set that is non-bonding electrons, right? But still a total of 3 sets of electrons. If we replace one of those bonds with a set of electrons, the set of electrons would occupy the position where one of the bonds was. So if I put a set of electrons here, kind of replacing the bonding set that was kind of pointed straight up, right, that really doesn't change the angle that you see right here. And there's still 3 sets of electrons. So the electron geometry is based on, you know, how many sets of electrons are there. That's still 3. This is still trigonal planar in terms of how the electrons are interacting because of the 3 sets of electrons. The angle here is still 120 degrees, but let me put a little tilde in front of the 120. You can have slight differences, right? In some cases, the lone pair will take up a slightly different amount of space than one of the bonding sets, etc. So this angle will vary a bit. It could be a little bigger than 120, it could be a little smaller than 120, but it's right around 120 in your molecule. Now here, for the molecular shape, when we talk about molecular shape, we do not consider where the electrons are, right? So I have these electrons drawn here as if they're kind of pointed out the way a bond is. Those electrons really are still associated with that atom though. So we describe this shape based on where the atoms are. So the shape is there. Now I look at that and I think this is a boomerang and that we should call this boomerangular. In terms of describing the shape. Now, sadly, that has not caught on with the wider chemistry community. The common name here is angular. Right? It seems like it has a lot more character if you put the boomer in front, boomerangular. But this is an angular molecular geometry. Now, sometimes this is also just referred to as bent, just indicating that it's not linear, it's not a straight line, that there's a bend between the bonds here. Now, to get this particular molecular geometry, right, we need a central atom that's going to have 2 bonding sets and a lone pair still. So a good example here would be sulfur dioxide, or SO2, right? And in this case, we'd have the sulfur in the middle, and what you'd end up with, right? I'm not going to go through all the bits of drawing the structure, but you'd end up with 2 double bonds to the sulfur and a non-bonding pair of electrons on the sulfur. So that would be 10 electrons on the sulfur, but sulfur is in a position where we can have an expanded octet if we get better formal charges, and you'll see all the formal charges are 0 in this molecule. So double bond is 1 set, the other double bond is the 2nd set, the lone pair is the 3rd set. Right? Those electrons are in those same 3 positions. The bonds are 120 degrees apart. Right? But this isn't quite a trigonal planar shape, it's an angular shape. Okay. All right, let's move on and start the discussion of 4 sets of electrons. We will not get through 4 on this video, but we do still have a little bit of time that we can start to talk about 4. So, if we have 4 sets of electrons, right, we have this same issue of there are a few different possibilities. So we could have all 4 are bonds, so what I called a 4-0. And if you're watching the videos out of order, I'm explaining the nomenclature here sometimes as we're going along. So I've talked about what these mean already. I don't want to have to redo that every single time. So probably a good idea to watch them in order and make sure you're following exactly what's being described. So 4 bonds, no non-bonding pairs. We could also have 3 bonds, and one of them is a non-bonding pair. And then with 4, there's a third possibility of 2 bonds and 2 non-bonding pairs. Now, if we go all the way down to 1 bond and 3 non-bonding pairs, that's not a central atom anymore. If it just has 1 bond, right, it's maybe a terminal atom, but it's maybe also just involved in a diatomic molecule. So that is not a whole lot that we need to worry about any kind of shapes or angles or anything like that. Now, 4 is maybe a little more complicated because if we have 4 sets of electrons, the structure is not going to be planar anymore. But maybe, as you're at home, a good way to think about this, if you kind of stand up and you step forward with one leg, so maybe you step forward with your left leg, and then you move your right leg backwards so that one leg is out in front of you and the other one is out behind you, and then you put your arms up in sort of a Y, like you're doing the Y part of the YMCA dance. Right? You kind of have gotten your legs and your arms as representing maybe the 4 sets of electrons as far apart as possible. So the drawing would look like this. Central atom is here. Now I can show 2 of the bonds in the plane of the paper like that. The other 2 are, one is coming out of the plane of the paper and one is going behind the plane of the paper. So I'm going to use, there's kind of a convention of a dashed line and a wedge. The dash is meant to indicate something that is kind of going back into the paper. The wedge indicates something that's coming up out of the paper. So this one is in front of the drawing that I'm using. This one is behind the drawing that I'm using. And let me give you a 3-dimensional view here maybe, if that would help. Right. This is actually a shape called a tetrahedral. Right, so you can see it's a pyramid, but it's more specific than that. It's a pyramid where the bottom is a triangle and all 4 sides are exactly the same triangle. So it's a very symmetrical type of period called a tetrahedral for a 4-sided object. So there are 4 exactly the same sides. Okay. Now we'll have to keep talking about this, but I'm going to have to stop the video there because of time, and we'll pick up here talking about 4 sets of electrons in the next video.